Yeah, thanks for the introduction. Thanks for the opportunity to be here. It's really wonderful. So yeah, as Suzanne says, today I'll talk about high-impact, low-cost cosmology with balloons and small spacecraft. Let's see if I can go to the next slide. I can. Yeah, and I guess here's part of the Arizona State universe. This was about an hour from campus in the mountains. It's lovely. It's lovely to be in these beautiful grounds too. What I'll talk about today is that it's a lot of ongoing efforts to deliver transformative cosmology science return with small targeted space missions. And as Suzanne says, I'll talk about my view on how that, a little bit about how that goes. One core part of that is that we need to target new sensor technology development to make novel measurements needed to deliver the science. So this connection between the sensor technology and the science. And I argue that this approach that there's decades of heritage here, a lot of strong track record of success. I'll just whirlwind tour through a whole lot of missions here: IRAS, COBE, Boomerang, Spider, WMAP, and Spherex, just to kind of where I see this model kind of over and over again, and been lucky enough to be involved in a couple of these. Okay, so there's this common model I see across these small, high-impact cosmology missions. A lot of the teams will identify an astrophysical effect through data-driven theory work. So obviously, this all starts with theory, starts with looking for something, but that there be a strong integration between theory colleagues and instrumentation and engineering colleagues. Identify new detector and optical technology needed to enable a direct measurement. So this theory is no good unless we make the measurement. As I think Rito and others would have said, if this was easy, it would have been done before. So there's kind of almost inevitably going to need to be a new, somewhat lower readiness level technology to enable these new measurements. Otherwise, they would have been done before. Build mission hardware and software with a small, agile team. So I think part of what makes these smaller, focused missions work is the fun factor, right? That they're fun. It's a small group of people that get close to each other, become colleagues and friends. That makes this work and makes it fun. And just you want to leverage that tight integration among theorists, analysts, engineers, and then deliver the science. So that was all a little bit vague. I'll talk about Boomerang. This was a high-altitude cosmic microwave background, a cosmic microwave background mission flown on high-altitude balloons in the 90s. Really, really impactful, late 90s, early 2000s. So how does it exemplify these common elements? So the astrophysical effect and the theory work. Suzanne presented a lot of the basic physics here. But before this mission, there was a numerical code called CMB-FAST that some data-driven theorists developed that would predict what this whole class of experiments would see in different scenarios. So to have this on the table to get before you get going, and to be friends with those people too, have them on the team. What was the new technology Boomerang needed? Millimeter wave bolometer cryogenic detectors. So these were new types of millimeter wave radiometer detectors that were kind of new, not flight proven in the 90s, but they were a whole lot more sensitive than the amplifiers that came before. And so the fact that it's a balloon mission kind of lets you tolerate a little bit of risk here, right? And it's a small focused team to make it work, even though it's risky. So this was the new technology that enabled the measurement. Or rather, it was the improved sensitivity. The agile team, the integrated team. So any kind of aerospace or remote sensing system is going to need systems engineers, designers, hands-on technicians, managers, data users. The thing is, in my definition of these small teams, is a lot of these roles are often the same people on these small teams. Maybe not all of them at once, although maybe a couple people, but maybe let's say at least 2 roles you find yourself in. And so the fact that you have at least 2 halves of your brain, yet you are wanting to make this mission work, like it facilitates conversations, it helps you understand each other, maybe kind of blurs some of these boundaries but focus on the big picture. So I think this kind of, I suppose it's interdisciplinary isn't the right word, but like having yourself in multiple roles in a team, there can be fun there, especially if you all trust each other. And then this all comes together to deliver the science. So the budget on this was definitely small under most definitions of scientific budgets. This was a few $1 million program that NASA supported. And it delivered a Nature paper at the end, and a rather transformational one. Like, this is a small focused team, small focused budget, and you discover something fundamental about the nature of reality. You discover that the universe on the largest cosmological scales is flat. Like, this was a major open question, and they just resolved it as a small team. It's really incredible. And this author list kind of includes people from all these roles. Like, this is an author list, but it's kind of everyone, which is sort of amazing if you think about it, that like this small team could have done something like this. They weren't the only team in this space. I'm leaving out other small focused teams that were going after this same question in those same days. But like, I think they all followed this model, Maxima or any number of others. So, and then when I started graduate school, I was kind of lucky enough to be on the tail end of Boomerang, but the high altitude balloon mission to measure the microwave background that I was lucky enough to be on was Spider, kind of pretty much a direct follow-on to Boomerang. So, same story, right? We're going to continue to explore the cosmic microwave background with high altitude balloons. And in the end, we delivered a world-class upper limit on the gravitational waves generated by inflation from the Big Bang. Suzanne and Rita went over the physics of that kind of thing and the exciting additional searches. Spider is clearly far from the only one working in this space. But what we really wanted to see from high-altitude ballooning in Antarctica is the picture of the penguin. So like, that's what this is all about, people, is the penguins. I did not get to see this penguin. I was home when this picture was taken. Dang. So maybe next time. And so again, we became friends. We all had multiple roles. New technology is what enabled the measurement. So I think we exemplified a lot of these traits. Another one, WMAP. This is a NASA satellite to measure the cosmic microwave background. I'm told from, wasn't lucky enough to work on WMAP, but again, from talking with friends and colleagues, same story, small focused team. 150 million is a lot of money, but compared to big science like Large Hadron Collider, things of that nature, this is small relative to those at least, and certainly focused relative to those at least. And so WMAP in its day was able to leverage new technology, new science analysis approaches to precisely test key aspects of standard cosmology. So this mission was building on COBE and Boomerang, other missions that went before. It's hard for maybe to remember or to realize, like, the discovery potential for WMAP was huge, because this was the days before. Like, the standard model of cosmology wasn't standard yet. This parameter space was wide open. Perhaps the standard model was conceptually wrong. These were all ideas on the table before WMAP. So this mission was sensitive to stuff that's kind of, now it's known to be non-standard. I'll just list it off. Non-trivial topology, a non-inflationary Big Bang, isocurvature perturbations, non-Gaussian perturbations, non-cold dark matter, these ideas that were really plausible before WMAP, and WMAP just really probes them very well with its, it goes to L2 in the solar system, makes maps of the microwave sky at a lot of different frequencies, crunches those in analysis to a clean map of the Big Bang of the microwave background, and then crunches that map into, well, if you analyze it in the paradigm of these non-standard things, they don't show up. If you analyze it in what is now known to be the standard paradigm and verified by experiments like this, you get measurements of the age of the universe and how much dark matter there is, so on and so forth. You're seeing what we now know are standard processes. So you could get down on yourself and think this is boring, or just realize that, like, discovering the standard model was and is a huge discovery. So this was a groundbreaking science return on a small budget with this focused team. Okay. I guess to get closer to me personally, again, I told you about Spider I worked on in grad school. Recently, I've been involved in another NASA mission. It's the Spherex satellite mission. It's led out of JPL and Caltech. Again, is this a small mission or not? Well, it depends on whether you think $400 million is small or not. I certainly think it's a lot of money. But again, compared to truly big science, this is a small, focused team. Same. There's some new technology we're leveraging. Linear variable filter technology is what's letting us measure cosmology, galaxy formation, and planet formation in this single optimized mission. And we do that by mapping the entire sky, this time in the near infrared. So take off radio astronomy hat, put on the infrared astronomer hat. So we map the whole sky in 102 colors with 6 arcsecond resolution. This is a lot of data on the whole universe and all these, lots and lots of galaxies. A core part of the mission is we'll release this data publicly very soon, by the way. So that's, this is a legacy product for the community, just the data itself. At ASU, I'm leading the team that develops the optimal sensor tasking algorithm that we need for this mission to plan the observations. Because it's a lot of data to be taken, and it's from low Earth orbit, which optimizes the cost and the operation aspect of it. But the downside is, from low Earth orbit, you can't look at the sun, can't look at the moon, can't look at the Earth. Got to pause for downlink, pause. But so there's a lot of things going on. Yet you have to execute the mission, right? Take data in an efficient way. So we have an algorithm at ASU that we've written into software, and we turn deploy it on the ground system computers at NASA JPL. So yeah, and this mission leverages heritage from WISE and IRAS. We're addressing these really important questions with this targeted budget. So to geek out a little more on the science, if you'll allow me, there's a lot of science here, just on the cosmic inflation, cosmology part of it. The idea is with these all-sky maps and all these colors, we will identify the 3-dimensional positions of millions of galaxies across the whole sky and out to a reasonable redshift of like 2, let's say. So the X and Y position, in some sense, will just come from, well, where is the blob? I see a bright thing over there. And then the distance comes from the fact that we measure a spectrum for every last object in the sky. And it's from that spectrum we can get the distance. We get this 3D distribution of the galaxies. It was the Big Bang that put them there in the first place, in some sense. And so by measuring this fancy graph on the x-axis is consider it to a pair of galaxies. How far apart are those? And then the y-axis, how often do you find pairs of galaxies that far apart? So the error bars, the little boxes, are this exquisite precise measurement Spherex will make based on this 3D data. And then the theory curves are 2 different scenarios. In one theory curve, we have kind of boring cosmic inflation, where it's perfectly Gaussian process all the way down. And then the simulated data here is in the case of a somewhat non-Gaussian process. And so this is incredible that we can probe physics powering the Big Bang itself based on these galaxy measurements. In the context of the gravitational wave measurements that Suzanne and Rito told us about, these are really great. They're actual science experiments. We're not just setting upper limits all day long forever. What's cool about measuring the same process in different ways, both in microwave and in infrared galaxy surveys, is it makes it into a science experiment where we will learn something from the next round of data. So I've kind of gamified out a couple possible ways this data could land. If we don't see gravitational waves, but we do see non-Gaussianity in our galaxy maps, this shows that inflation followed a multi-field process. There's a model of inflation we will have discovered if that's how the data lands. Vice versa, if we see inflationary gravitational waves, but it looks really Gaussian in our galaxy data, that's also a discovery for the community. That shows that single field inflation was the process that powered the Big Bang. In the no-no or yes-yes scenarios, this is a challenge to the paradigm. Like, there's not a kind of plain vanilla, just a whiteboard or 2 inflationary models that yields the bottom 2 outcomes. And so we will have learned that we need to reevaluate the paradigm if that's the outcome. So no matter what, we learn a lot, and that's what makes it a science experiment. It's really exciting to see where this field is going to go. And this is geeking out on the software. So this optimal sensor tasking algorithm we have at ASU to keep within our, just this blue kind of half moon shows the avoid the Earth, avoid the sun, so on and so forth. We have to stay in the allowable pointing zone, yet take our data. So that's what we develop at ASU. So yeah, so I talked about this model of small teams, new technology, integrated teams. And a couple missions that I've been involved in that do this and just make it really fun and really productive. This was some brainstorming about where could we go with this. So how could we use this approach as a community here in the room and in the international community to build future missions that follow this model and meet our needs for the science goals we have as a community. So I can just, the pictures show some of them. The idea is that to start at least, think of a specific science goal and then think of a technology that's an enabling technology. And then we can build the missions from there. So we could probe star formation with new infrared detectors. We could look for light curves to measure the activity of stars and the exoplanets around them, on a CubeSat that's currently being done. We could do 21-centimeter radio maps to probe star formation, structure formation. We can do whatever we want as a community, especially if we think it through, and identify enabling technologies that we need to achieve our goals and meet our requirements that we develop. So this is just some brainstorming we can talk about over the panel if it's interesting, or over coffee with me later. But there's lots of things we could do together. Anyway, so yeah, to conclude, again, it's really great to develop small space missions to deliver transformative science impact with low cost, and to do that with small integrated teams. This approach has lots of heritage and lots of success, and it'll let us explore the universe from the Big Bang to exoplanets together. So yeah, thanks for your attention.